Welcome again to databases. Last week we covered some of the introductory material, basically hopefully getting everyone up to speed on some prerequisite knowledge. Today we're going to continue a little bit more on that front, and time permitting we're going to move on to actually implementing some of these cool things in actual systems and some of the concerns that arise when trying to do so. So once again, today we're going to finish up, hopefully, our discussion of SQL with a couple of additional topics. And yeah, couple of pieces of news. First off, the Project Checkpoint 0 deadline officially was last night due to a small typo. Submissions are still being accepted until tonight, but given, I hope nobody found that particular assignment very difficult. So if you haven't submitted this yet, please give me a shout, or please submit, or what have you. We'll be posting the description of Project Checkpoint 1 tonight. Have a look at that. The deadline will be about 3-ish weeks from now, and you don't necessarily have to start implementing it yet, but I would encourage you to take a look at it as soon as it's posted. And I'll be making an announcement via Piazza for that. As was mentioned on Piazza, the Homework 1 deadline is now Wednesday night. And if you've been following Piazza, there's also now a couple of videos posted of prior lectures. I'm going to try and keep these videos posted within a week of the lecture being presented. One last thing I wanted to mention. So some of you may know this, some of you may not. I periodically bake things and bring them into the department. Normally these go pretty quickly. However, as a motivation to get you to discuss various topics on Piazza, I'll be, over the course of some of these lectures, like I did on last Monday, mentioning that this particular piece of group work, please start discussing it on the forum. So as additional motivation, I'm going to say that I'm going to pick 1 or 2 posts, give or take, each week, contributing to this group work business, and if you are one of those couple of posts, you'll be receiving notifications that there are baked goods in the department. A little bit of incentive, I hope. All right, so let's get to it. We talked last Wednesday about a couple of different relational algebra operators. I'm proud to report that the aliens have returned the select operator. As you can see. So there are a couple of basic operators that sort of form the foundation of just about everything that a typical relational database does. Selection, projection, cross product, set difference, and union. That together with aggregation, which is kind of a form of projection, form basically anything that a database can do. Nearly anything that a database can do can be expressed through some combination of those operators. There's a handful of other operators that they're purely for convenience, intersection, join, division, renaming, but the core concepts, the core constructs can all be expressed through those 5 basic operators, as well as aggregation. So, just to recap, let's say you had this particular piece of data, and you had a relation that stored all of your captains, as well as the location of their ships. Oh, sorry, captains as well as this particular location relation here. One thing you might want to ask is, find me the last names of all captains on a ship currently located somewhere in the Federation. We can express that as a query, and we can express that query in terms of various relational algebra expressions. So we have a relation representing all of our captains. We have a relation representing the location of their respective ships. And then we have another relation that gives us the affiliation of every planet that we have. And so we need to do, in a sense, a three-way join here to figure out which captains are located which captains are on a ship that is located in the Federation. So once again, we can express this as a query, and there's a couple of things to note about that particular query. In particular, that there are potentially more efficient ways of expressing that specific query. So, off the top of your heads, can you think of any reason why this particular query might not be as efficient as possible? Or any ways that you might potentially improve on the efficiency of this query? In back? Was that a... No. So, what could lead, generalizing the question a little bit, what could lead to inefficient query evaluation? Lots of joins? And why, let's get even more to the root of the problem. Why are joins bad, or why are joins expensive? They compute the Cartesian products, and that produces a lot of data. Exactly. So one of the big problems with these things is that they're one of the core problems that databases exist to address is just moving data around. You want to, when you evaluate a query, you want to evaluate it in such a way that it minimizes the amount of data that you have to move around. Minimizes the amount of data that you have to process and move around. So how can we reduce the amount of data that this particular query has to move around? So in general, what are the two ways that we can reduce the amount of data that we're moving around? Yes? Projection? Yes. So one way to reduce the amount of data that you need to move around is to project certain columns away. Now each of these relations has a large number of columns. And in particular, affiliation has two columns, only one of which is relevant for the selection predicate. And as soon as you evaluate that selection predicate, you can get rid of that particular column. As soon as you join it with location, once again, there's only going to be one particular attribute, namely the identifier of the ship, that you need to join that particular relation back to location. So to sort of evaluate this query in the most efficient way possible, we want to minimize the amount of data that we store. We want to minimize the amount of data that gets materialized as we evaluate it. Okay, so we talked about SQL on Wednesday, and in particular we focused on how do you use SQL to query data? How do you ask questions about data? But one thing that we didn't cover is how do you manipulate data? How do you express properties of data that help you when you're trying to manage that data and actually keep it consistent as it's being changed and updated? So sort of the fundamental, the core construct that we'll be talking about today is the create table statement. Just to recap, the create table statement defines a schema for a particular relation, defines all of the attributes as well as the domains that those attributes belong to, whether they're character arrays or integers, or essentially what kinds of values they can take. As an example, a 20-character string. SQL defines a handful of different operations that let us manipulate these schemas. So we can create relations, we can destroy relations. We can also alter relations as well. SQL also gives us the ability to insert and delete tuples and essentially manipulate them. So as a bit of group work to get you into the, to get you going today, let's turn to your nearest neighbor, and I'd like to, write together, write out a query that will compute, given this particular schema, the name of all officers that have at least the mean number of years of service, where mean is an aggregate operation that you have access to. All right. So, how would I express this query in SQL? In there, in back, was that a hand? Yes. Okay. Well, what am I doing here?
Yeah, select average years of service from office.
All right.
We will have a second query, select name and years of service in the second query.
In? What's next? Where? That? What's missing? What's missing? From? Okay, there's a from missing. What else? There? Okay. Okay. As a warm-up. One more warm-up. What's the following query compute? Yes, in the back. Good. Now, here's a bit of a question. What if we knew the specific set of values that rank could take? Would that make evaluating this query easier? Let's say we knew that there were only 8 ranks. Could we use that information? Yes?
Well, if you were doing the query evaluation and there were a lot of people and you got like 8 different ranks, you could stop there and know that there was nothing else left to go through in the table to get more information.
Okay, so if we were scanning through the entire relation, we would know when to stop early. And as we'll soon see, there are a couple of other ways of taking advantage of this, depending on how the data is stored. So, okay. This ties into a slightly deeper question, which is, what exactly can a database make use of? How can we give a database information that it can make use of to store data more efficiently? And that's pretty much the sort of central bit of this lecture. Databases are relational databases in particular, are designed to make use of a number of different properties about data that, well, first off, help them be more efficient, and second, that help make sure that the data is correct and consistent. A typical relational database so in a typical relational database, you don't necessarily want to have data. You want to make sure that your data is clean, is well organized, is correct. And in order to ensure that the data is correct and that it stays correct, a relational database will allow you to define a set of properties called integrity constraints that define what it means for a particular data value to be correct. These typically have the form of existence predicates or uniqueness predicates. So there should be only one of the following data type or one of the following value in a database. There should be only one person with a particular UBIT. There should be only one person with a particular social security number. And the bulk of these constraints that we're going to be talking about are of that form. There's a handful of different types, to be a little more precise about that, there's a handful of different types of integrity constraints. So there are domain constraints which represent essentially type information. So we mentioned the possibility of there being a fixed number of different ranks. We could define a domain that represents the possible set of ranks that an officer could have, and that any rank that fell outside of that domain would not be valid. The database would be able to reject that as invalid and sort of help you avoid creating corrupted data. The second type is called a key constraint, and this essentially enforces that a particular attribute or group of attributes should occur. Any given set of values for those attributes should occur at most once. Related to this is this idea called foreign key constraints. And a foreign key constraint essentially says that there should be that a particular attribute references another relation. These are analogous to the arrows in the entity relationship diagrams that we talked about last Monday. A foreign key constraint basically says, okay, I am referencing that relation. This particular row includes a reference to that relation, and if I'm referencing that relation, there had better be something that I'm pointing to. And finally, we can have much more general constraints, which are called table constraints. And these can be really anything you want. SQL essentially gives you the ability to define a query, the results of which determine whether or not the constraint is satisfied. So let's start with the first of these. Domain constraints, essentially, you can think of these as enums or type defs in C, or Java enums as well, has enums as well. The idea is basically that you define a type and put some constraints on the possible values of that type. For example, the rank of an officer has to fall within a particular range. Lieutenant, captain, admiral, what have you. And so when you're defining a relation, you can also define when you're defining a relation, you can you can also create what are called domains or types. Different systems have slightly different syntax for this, but you can define a type that constrains values belonging to that type to a certain range. There's one particular domain constraint that you'll, if you're using SQL, you'll encounter a lot, and this is called not null. So normally a SQL relation, any value can be null. The not null constraint basically says that that value can't be null. This is often used when there's a very strong assumption that a particular value is defined. So for example, if I have a table listing officers, the officer had better have a unique identifier. And if they don't, then that's a deeper problem. They might not have a last name, but they'd better have an identifier. Key constraints are essentially a way of saying that a particular set of attributes has to be unique and has to define a unique value. So for example, there may be two different officers named James, but there had better only be, in this particular example, we can say that no two officers born on the same day have the same name. So we can say that name and birthday form a key for this particular relation. It might also, because birthday is related to age, we can also say that name and age form a key for this relation. So either of those are actually valid constraints here. The term key specifically has a slightly deeper meaning, and a key isn't just a set of attributes that uniquely identify a particular tuple. A key is So in the example I just gave you, birthday and name form one key. Birthday and age, sorry, name and age form another key. Conceptually, you could also think of birthday, name, and age together forming a key. This is somewhat bad practice, as there are two different subsets there that also form a valid key. I could break down name, age, and birthday into just name and age, or just name and birthday. And both of those would be valid keys. So the term key in particular refers to a minimal subset of attributes that define, sort of uniquely identify a tuple. SQL, of course, has a way of specifying these, and there's a couple of different ways that this happens. So relations typically have what's known as a primary key, which is sort of the canonical way of identifying that relation. If there's an identifier column, for example, that not only uniquely identifies the tuple, but that also is the best way of identifying that tuple. And so at the very end here, let's see, does this work? No. Right. So by adding the clause primary key, that effectively defines that particular attribute as the canonical way that I'm going to access or uniquely identify tuples in this relation. There's also this idea of unique, which is more of a validity constraint than back up a little bit. Primary key actually has a significant impact on how the database is going to manage the data. Because you're telling the database, I am always going to access this tuple by this particular attribute, it's actually going to reorganize the data in such a way that it can access the tuples of that relation much more efficiently. The unique property identifies a key constraint, but the database treats it as a little bit less important. So it'll enforce that particular key constraint. If you try and insert a second tuple that violates it, it will complain about it, but it won't necessarily make any organizational changes based on that additional information. Conversely, primary key identifies the canonical way that you access elements of that relation, and will actually dictate how the database organizes the data. You can also assign names to these constraints. You can give them a name to make them easier to modify and manipulate down the line. So, any questions up to this point? Yes?
If I add a keyword after the unique, does that make a difference?
Off the top of I'm not immediately familiar with what that would do. So the question is that some database systems have the syntax unique key and then a set of attributes, and whether that will make any change on the database's behavior. Off the top of my head, I don't know the answer to that. I'd be happy to look it up, and if you ask the question on Piazza, I will respond. I believe the answer is no, but again, ask the question on Piazza and I'll get back to you. Anything else? Yes?
Why would you name a constraint? Why would you require a name?
It doesn't require a name, but oftentimes when you're manipulating schemas, so the very beginning of the presentation I had, I mentioned that there was one command, alter table. You can alter constraints as well. So you can add a constraint to a given attribute, you can remove a constraint from a given attribute, and if you have a name for the constraint, that makes it much easier to reference. Does that address your question? Anything else? Yes?
When you define a unique key, you cannot accept null values because primary key doesn't accept null values. So when you define a tuple as a primary key.
Yeah, I believe if you define something as unique or definitely a primary key, probably also unique. So the question is, can you have null values for a primary key? No? Oh, can you have null values for unique? I believe the answer is no, but again, ask on Piazza and we'll get back to you. Yes?
So, try to insert something, but it doesn't meet the constraint, like there's something already in there that has the same name and age, say, what happens?
So the question is, if you insert a tuple that would violate the constraint, the answer is that the insertion won't happen. Slightly more generally, you can group a bunch of operations into what's called a transaction. We'll talk about those a little bit more further on down the term. But the idea is that if at the end of the transaction you have a relation where there is a constraint violation, the transaction will be aborted. The transaction will fail. So you could potentially, as part of one transaction, insert a tuple and then remove the other tuple that would cause it to conflict. And at the very end of that transaction, it could the system would recognize that as acceptable. But just one insertion as part of a single operation transaction, a single insertion that caused a violation of a constraint would fail. Does that address your question?
Yeah, I mean, it'll give you some sort of like feedback.
Yes. Yes, in fact, that's another reason that you might want to name the constraints. It'll alert you usually with the name of the constraint that got violated. Anything else? Yes?
If we enter the table and change the primary key afterwards, then does the database changes the structure of storing the data?
Depends on the database, but typically the answer is yes. The primary key, as I said, defines the most effective way that you have of identifying a specific tuple. So the database is so a typical database will organize the data in such a way that it can very efficiently access that particular key. Typically, this means either storing the data sorted or in some sort of tree structure. And again, we'll get into that a bit in the next 3 or 4 lectures. Yes? Sorry, could you speak up a little bit? I can't hear you.
Suppose we have like data table with the set of certain attributes and constraints already defined, and we have a certain set of tuples in it. Then later on, suppose we alter the table and we modify the constraints of some of the attributes. So already some of the tuples which are inserted, suppose if they are violating the conditions, so do they get deleted or like what?
So the question is, what happens if you change the properties of a table by adding a constraint that is not violated? What happens if you have a existing relation and you add a constraint to it, but the constraint is not satisfied when the relation when it's first applied to the table? The answer is that, again, this depends on specific database implementation. The general rule of thumb is that altering the table is also part of a transaction. The general rule of thumb is that a database won't allow you to commit a transaction or won't successfully commit a transaction that includes, that ends up with a violated constraint. If it's because data was added that violates an existing constraint, you go back to constraint but no data. And if the if there's data but no constraint, and then you add a constraint, it'll go back to data with no constraint. You'll basically be required to fix the data before you apply the constraint. But again, this depends on specific implementation. It may, the system may ignore it. It may choose to do some data management of its own. That's typically less likely, though. Yes? So different databases have different ways of representing constraints. There's a variant of, so essentially the effect of what you're trying to achieve here is that if a particular situation occurs, you want an error to occur instead. If a particular operation would create a specific condition in your database, you want an error to occur. So as several people have noticed on the forums, MySQL doesn't have support for, or has more limited support for constraints. One way to work around this is to use what are called triggers. And a trigger is, I haven't gotten to it yet, but it's kind of like a table constraint. It's a query that when a particular event happens, this query or this process gets invoked. And effectively all a constraint checker is, one of these what happens under the hood when you define a unique constraint is that a trigger gets generated, or several triggers get generated that enforce that particular constraint. Excuse me. Effectively, every time you insert something or delete something from the relation, you need to run some constraint validation code. And typically what will happen in most database systems is that this, for example, including the word unique in there, is shorthand for and create a trigger that enforces this particular constraint. Does that address your question? All right. Yes? Speak up. Depends on system implementation. So the question is it the case that when you define a constraint, a trigger gets generated? It depends on the system. I know Postgres does this. I'm pretty sure Oracle does it as well, that constraints are basically implemented using the same code paths as triggers. There might be some minor structural differences, but I believe at least in Postgres, if you define a constraint, Postgres will just go on and create a set of additional triggers for you. All right. Okay, so we talked on last Monday about entity relationship diagrams. And one of the aspects of an ER diagram was this idea of a relationship, or two different entities being connected by some sort of relationship. So the way that gets represented in SQL is that you have a constraint that indicates that a particular attribute references another relation. So for example, I have a table of officers that are entities and a table of planets that are also entities. One particular way of implementing a many-to-many relationship is to actually create another relation for that purpose. And that table is going to include a reference both to the officer, so every visited relationship is going to include both an officer, the officer that did the visiting, and a planet, the planet that was visited. And there is now, obviously, if the officer goes away, then that particular visited entity, visited relationship, is no longer relevant. If I, or at the very least, it's pointing to some non-existent officer. And I'd like to make sure that it's always pointing to something valid. I don't want to delete a, think of this as memory management in C. I don't want to free memory that I'm pointing to. And so foreign key relationship effectively does this. It allows me to indicate that I have a particular attribute that is referencing an attribute in another relation. Any questions on this? Great. Note, by the way, that you can always have the attribute reference itself. The table reference itself. And if it turns out that there's a particular attribute that the attributes are not named the same way, you can also indicate which attribute is being referenced by parenthesizing it after the relation that is being referenced. All right. Now if you look at this particular ER diagram, does anyone see an immediate problem with this relation in this particular set of constraints? Yes. Commander can have the same ID. Sure, a subordinate could potentially, or a commander could reference themselves as a commander. Okay. If I'm understanding you correctly, correct me if I'm misinterpreting. The very first tuple that you insert is not going to be able to reference any other tuples. Indeed. So the problem with this particular relationship is that oh, I'm sorry. I'm losing my place. There's actually two different problems, and you both have hit on individual problems in this particular ER diagram. So the first is, yes, that the subordinate, each officer can only have the officer is explicitly referencing their specific subordinate, and that's a problem because that means that an officer can only have one subordinate. So you typically want to have many subordinates. Foreign key relationships work for one-to-one or one-to-one or many-to-one relationships, but not so well for many-to-many or one-to-many relationships. And the second is that at the very top of this entire hierarchy, you have a problem because you have to have a commander, and that commander has to point to something valid. But if there's nothing valid to point to, then the foreign key constraint is not going to be satisfied. Okay. The way you kind of get around that, so the way you get around the first problem is to simply remove the foreign key constraint. The way you get around the second problem is that you're allowed to have foreign keys which are null. So if you're not actually pointing to something, then it's valid. Okay, so we already kind of covered this. If if there's an insertion, deletion, or update that would cause a violation of a trigger, of a constraint, the operation is pretty much just rejected. An error will occur. Constraint X has been violated. There's a problem. Now, as I said, there's three basic operations on which you have to enforce: insertion, deletion, and update. Now, we talked about three different classes of constraints: domain, key, and foreign key. Why is it the case that we can ignore two of those on deletions? Yes?
Well, because deletion, you're just looking at a couple, so you don't really have to check whether the thing is going to, but the key is the same, right?
Yep. So, exactly. If you're inserting a value, domain constraints essentially say that you have a value that is belongs to some domain. But if you're deleting data, well, there's no new values to check. And similarly, key constraints say that you can only have one instance of a particular, at most one instance of a particular data value. So if you're deleting it, then you're decreasing the number of instances at worst. Okay. So this is effectively how a database is going to enforce the basic types of key constraints. There's foreign key constraints, on the other hand, create a fairly tangled web of pointers. Anyone who's tried to debug memory leaks in C can easily attest to the fact that following pointers is often quite painful. So what databases, one other feature of SQL is that you can enforce these foreign key constraints not just by rejecting the update that violated them, but actually by modifying the data in some specific ways. So as an example, if I delete a value that is being pointed to, I can delete everything that is pointing to that value. That essentially keeps the database consistent. It keeps the data correct. It just operates in a slightly different way. Where are we? Yeah. So far we've talked about just outright rejecting operations that right. So this basically boils down to there are three different possibilities that could happen. Possibility one is that we insert a tuple that references a key that doesn't exist. We're pointing to something that just outright doesn't exist in the first place. The second possibility is that we have a tuple, or we have two tuples, one of which is referencing the other, and we delete the reference tuple, and we have to be able to react to that. And the third possibility is that we have that one of those two tuples gets modified. That is to say, the tuple being referenced gets modified. So how should we react to a tuple being inserted that points to something that doesn't exist? Reject it, yeah. There's really nothing that you can do at this. There's no obvious changes to the database that will make this sane. What about, what if we delete a tuple that has been referenced somewhere else? Can I get a hand? Yes? So don't allow the deletion to happen. Reject, as before. Okay, so that's one. We have one strategy. Can we do? Yes. Okay, so two more strategies. We can delete the tuples that are pointing to that particular value, or we can replace those pointers with null pointers. Great. So, well, delete all referencing tuples. We can disallow the deletion, or what about if we change the value that we're referencing? Yes.
See if it's been changed to some of the tuple which is already there.
So in this case, we have the problem that we have is I have PR diagram here. I have visited, which references another relation, and the problem is that I'm renaming a planet. So what can I do about that? Yes?
It's equivalent of deleting the planet and adding a new planet.
Okay, so one strategy would be to do exactly what I did before. Replace, I had three different strategies. I could either delete all the referencing tuples. I could reject the operation outright. And the third approach was to replace the referencing pointer with null. Now that last one sounds a little bit aggressive. Is there a cleaner way? Yes?
Replace the referencing pointer with whatever the new updated value is.
Yeah. So same exact three strategies. The only difference is that because we're not deleting the value outright, we have something else to point to. So we don't have to replace it by null. Okay. So yeah. Good. So the way that this gets encoded in SQL is that you have, in addition to the foreign, as part of the foreign key constraint, you can also define a set of reactions to take. And these are always phrased as on delete, do X, on update, do X. Where X is one of either cascade, no action, or set default. The first of these will essentially propagate the change to all of the referencing tuples. The second is going to just outright reject the triggering operation, and the third is going to allow you to replace the value with the referencing value with some default. Any questions up to this point? Yes?
Is it mandatory that foreign key constraint refers to a primary key of some other thing?
It doesn't have. So the question is it mandatory for a foreign key to reference a primary key of another relation? It is, again, depends on system implementation. In general, it's not mandatory, but it's recommended. Because of the fact that primary keys, the database knows that that's sort of the canonical way that you reference individual tuples. Because of that, it makes it much more efficient it makes it easier for the database to be efficient, but it's not. I don't believe it's strictly required in most systems. Anything else? All right, cool. All right, so moving on. There's a couple of other things that you can do with constraints, a couple of other tricks. Now, constraint validation can be fairly expensive. Determining whether a particular value is unique is, well, it's, at the very best, a log n operation. And if you're inserting a very large number of tuples, determining whether all of them are unique can be actually quite expensive. So SQL provides a facility by which you can defer evaluation of these constraints. And you may have noticed that there's one constraint clause that I haven't covered, and that's these table constraints. So a table constraint can be pretty much anything you want it to be. And the official SQL syntax for this is that you can put the word check and then in parentheses an arbitrary Boolean expression. And ostensibly, every single time the query is, the relation is updated, that particular constraint will be validated. If the constraint returns false, then that operation will be considered to be validating. So, for example, here, what's this query saying? Yes, so this is this particular constraint is saying that the officer's ship cannot be named Enterprise. So you can insert as many officers as you like, but none of them can be on the Enterprise. And after, well, conceptually, after any update to the database, this had better be true. Depending on implementation, this may not be validated after every single insertion. So here's another example. These check constraints don't necessarily have to apply to specific rows of the relation. So for example, if I want to make sure that there's always at least 100 planets and space stations in my database, what I can do is insert a check constraint on the space stations relation so that I can never delete space stations to the point where there are fewer than 100 of them. Now, there's a little bit of a problem with this particular phrasing of that particular constraint, which is that the check constraints, the table constraints, only get applied when a table is updated or modified. Could this constraint be violated ever, the way this is phrased? Or could I create a database where this constraint was through a series of update statements or update, delete, insert statements, could I violate this particular constraint or cause this constraint to be violated? Okay, so the constraint is on space stations, and it will be checked every time space stations is modified. So what I could potentially do is delete from planets, and if I have fewer than 100 space stations, I could end up with this constraint being violated. So more generally, what I can do is SQL also provides a assertion capability. And again, this is progressively, we're getting into progressively less supported functionality in general, but Postgres, Oracle, practically every commercial database supports this feature, where you can define an assertion, and after every single transaction or every single operation, depending on how this is implemented, this particular query will get run. And if that query fails, then the operation or transaction won't be allowed. And not just operations on a particular table. So any questions up to this point? Any questions on constraints in general? All right. So that's basically constraints. One other little bit of SQLism that I'd like to get into today is a variant of joins. Now, first off, does everyone know what a Venn diagram is? Yes. Okay. So I'm going to use a Venn diagram to illustrate this additional this last bit. So I have a table of officers and I have a table of joins, and ostensibly, a table of planets visited, and ostensibly, there are some officers that have never visited a planet, and depending on how I've set up my constraints, there may be some visitations that have not been by any officers that I'm aware of. So when I do a join, I'm going to return every pair of officer and visited that matches up. If I join if I do a natural join between these two. But there's also this whole space of officers who may have never visited any planet. So what if I wanted to? Someone may have read up on this. What if I wanted every single officer, regardless of whether or not they've visited a planet? Anyone know the answer? Left, yes. Yep. So there's a variant of joins called called outer joins, which I just wanted to bring up briefly. That's what I was just asking. So let's say we have our fun little group of tables here. We have Kirk, we have Spock, and we have our ever-friendly red shirt. Kirk has visited both Vulcan and Earth. Spock has visited Vulcan. The red shirt has never visited anything, and probably won't, since they're going to get phasered within 5 seconds of appearing. Regardless, once you turn and amongst your groups, come up with a relational algebra that will produce this particular relational algebra expression that will produce this particular output from those particular inputs. And let's say 4 minutes. 3 to 4 minutes. All right, has anyone come up with a relational algebra expression that'll solve this? Need a little more time? All right, 2 more minutes. All right. I see someone's come up with a suggestion. Yes, in the back. You're going to need to speak up a little bit, but I heard projection.
Name planet. Officers, left outer join.
Ah, okay. You're skipping ahead a couple of steps. How would you compute it without using left outer join? Does anyone have a suggestion for how to start on this? Yes.
Well, you could start by getting all the names of all the officers, get rid of all the officers who had been planets, join those up with the null value, the second value, which I don't really know how you do, and then add in the result of the join between officers.
Okay, so start. So evaluate. Am I hearing you correctly that you would start with, you would evaluate it in 2 steps?
Yeah.
Let's start with the second step since that's simpler.
Okay. Projection of named planet from a join of officers and planet. Or sorry, business.
Okay. And then?
And then union that
there's a number of different formats for this. What I like to do is just include it as part of the projection. There's actually, use a slightly different. There we go. All right, projection of.
Selections from officers.
Select. What am I selecting? Speak up.
Selecting name from officers and then set difference of projection of name of officers join this.
Okay. And I'm going to save my chalk hand. Is that about what you were looking for?
Yes.
Good. So just to describe what's going on here, it's effectively the same idea. You start off by projecting, by computing the normal join result, and then you extend it with essentially the difference. So you figure out which officers are not part of the result. That's what this unjoined officer ID bit is doing. Join that back with officers to get the full set of officers that belong to that particular attribute, the full set of officers that haven't been joined. And then you just extend that whole thing with a null value, and you've got the rest of your relations. So, as people have been pointing out, this is a relatively frequent pattern. It's one that occurs not infrequently. So people have actually given this a name, outer joins. And there are three different types of outer joins: left, right, and full. The one that, as stated, the one that we're going for here is a left outer join. So just to recap, a regular join gives you all of the pairs that are in both sets. A left outer join will give you everything that's in the left set and the middle. Right outer join will give you everything that's in the right set and the middle. And what does a full outer join do? Yeah, everything. All right. We've got a couple minutes left. I'm not going to launch too deeply into the next bit of the lecture. Actually, first off, are there any last questions on SQL? Yes.
What if you wanted to only get the left or the right if there was nothing in the center? Or like either pair. Say you wanted, if you had something A comma something, you wouldn't want another field that also had like A comma something.
So you want everything that belongs to the left selection, but the left group, but not the right group.
Well, I would say you want everything that belongs to the left group only if there isn't something with the same left value in the center. Like say A is not a key or something. You might have a value that's A null and A B possibly. And let's say you want to have the A comma null if you had an A comma B. Does that make any sense? But let's say you didn't have A comma B in the center, then maybe in that case you would want A comma B. So you want A to be, or the first value to be unique, but you want to put a precedence for the pairs where the second value is not. Is there a way to do that?
I see. So the question is, and let me see if I get this correct. The question is, if you have multiple things that could possibly be joined, one of which would already create a null in sort of the tuple specific attributes, is there an operator that takes that into account?
Well, like, what's the best way of like processing? I don't know. Maybe my question is not making sense.
The short answer is that there's no specific operator that I'm aware of that does this. The slightly longer answer, I would suggest posting on Piazza, since the amount of, I suspect, large amounts of code will be involved. I guess that doesn't really address your question, but if you post it on Piazza, I will try to. Or anything else on SQL? All right, so let me just very briefly whet your appetites for the next set of the next general subject. What we'll be talking about Wednesday is essentially how do you store data. And really the main problem here, the main problem that we're trying to address is that there are a variety of different ways of storing information, and different mechanisms have different speeds, different computational properties. These have traditionally been organized into a hierarchy, the memory hierarchy, which goes all the way from the CPU registers all the way down to virtual memory. And maybe in the last 5 or so years, this has also been extended to the data center networks and essentially large clusters. You can see those as kind of a variant of the memory hierarchy. So for the cheesecake points, cheesecake tokens of the week, I'd like some discussions on Piazza. There's a variety of different classes of memory in this hierarchy. I'd like to see basically some discussion about what are the characteristics of each of these, and what their properties are, how you would access data on one of these, and more generally, how you would approach, or which of these are important to a data management system. So, all right, with that, any last questions? All right, see you on Wednesday.